Hello, this is Math Kimchi, and today we will be looking at the Mandelbrot set and how to implement it into Python. So, first, let me explain to you what the Mandelbrot set is. First of all, we have to understand that there are complex numbers, and the Mandelbrot set will be drawn in a complex plane, which essentially is a two-dimensional version of the number line, where the second dimension represents the imaginary side of things. So, in a normal number line that we're used to, uh, A just represents whatever number there is, and A is going to be a real number like 1 or pi or -3 or something like that. And in a complex plane, we also have b, and b is actually going to also be a real number, but b represents the imaginary side of things. So if we have a point in the number plane, and let's call it z, then the x-axis represented by the a, or the a represented by the x value of the point, is just going to show what the real value is, or the real side is, and b or y kind of shows the imaginary side. So what I'm saying is, if this was a complex number plane, then each of these points represent a number in a complex number. So for example, let's say this point, or let's start with this. This point is supposed to be the origin. So in terms of x and y, it's at 0, 0. And that would mean if a is equal to x and b is equal to y, then this number is just 0 plus 0i, and that's just 0. And the number line we're familiar with is just on the x-axis. So 1 would be somewhere here, and 2 is here. This is -1, this is -2, and as we said earlier, this is just 0. And now the y-axis is just imaginary numbers. So, well, this is 0 again. This is 1i, and this is 2i, and here is -1i, and here is -2i. And let's say we went somewhere outside of the two axes. So somewhere here is going to be 1 plus I, or 1 plus 1i. And somewhere here is going to be -1 plus I. This is going to be -1 plus 2i, and so on. So each point in here is a value, or a complex number, and in a usual graph that we're used to, when we're working with only real numbers, we have the x being the input, the x-axis being the input, and the output is represented in the y-axis. But in this case, we have both x and y axes being used up as the inputs. So the way we're going to display the output is going to be with color. So in this case, the black means that the point is in the Mandelbrot set, and the redder it is means the faster it approaches infinity, and the more blue it gets it means the slower it approaches infinity while still approaching infinity. And this might not make a lot of sense because I haven't explained the Mandelbrot set yet, so let's get to that. So the way we can tell if a number like z0 or just z is in the Mandelbrot set is by saying that z0 is equal to z, and so we now have a sequence with z starting the sequence, and to get the next term in the sequence we use this recursive formula: zn equals zn minus 1 squared plus z0. And a better way to say this is the new term is the previous term squared plus the zeroth or the original term. And if this goes on to infinity as if zn goes to infinity as n goes to infinity, then the term is not in the Mandelbrot set. And when I say goes off to infinity, I mean if it shoots off this way forever, this way forever, this way, any direction forever, as long as it doesn't keep on going towards the origin or oscillates in between finite values. And now how are we going to calculate this? Because we can't keep on doing this, running this equation infinite times in Python. So the way we do that, or the way we find if it's in infinity or not, is by calculating this multiple times. So at least 20, I'd say, for good accuracy, but I like to use 100 times. And if it ever escapes a circle, and the circle is centered around the origin and has a radius of 2, so if it ever escapes that, then we know that it is outside or is going to shoot off to infinity. But if it doesn't, we know that it's going to be finite, no matter how big n is. And the way we get the blue versus the red, the way we see how fast it approaches infinity is by seeing how long it takes for this for a term to escape, I guess, the circle. And a more concrete way of explaining this is, I guess, by just showing you guys how it works. So let's say we choose a point outside of the Mandelbrot set. So this is red, so we know it's going to escape really fast. So if we click on this point, we know that the next point is going to be somewhere here. And let me click on a point closer to the blue. So this weird shape, it starts off here, then goes here, 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 and so on. And it starts off kind of slow, but we see that it still escapes the circle, and we can see that with the other points that are blue as well. And I'm gonna restart this because it's kind of slow, or it's kind of messy now. But now if we choose a point inside the Mandelbrot set, if we choose a black point, then let's see. So we see that it starts off here, here, and then I think it goes here, and then it kind of homes in to this single point. And we see that a similar pattern for this as well. It spirals into this one point. But if we choose this point, it starts here, then goes back here, then it goes back here, and it keeps on doing that. So we see that it oscillates, and even though it oscillates, it doesn't shoot off to infinity because it's just oscillating to basically two same points, and it's not getting any further away from the origin. And for this one, we see that it oscillates between 3 points, whereas this one oscillated between basically 2 points. And I think that one oscillated between 4 points, and this one goes from here to here to here, and I'm not sure where it went after that, but we see that for all of the points that are in the black, never goes outside of the 2 radius circle, at least however many iterations we loaded in, and therefore it doesn't shoot off to infinity. So now let's look at the actual program. We start off by importing a system and Pygame, and Pygame is the program that we're running like the visuals in. And the reason we need a system is because in the loop we have this function or this line, and basically it checks if we have closed the Pygame window, and if we did close the Pygame window, then it's just gonna turn the program off. So this one's not really important, and Pygame is kind of important, but not for the actual math itself. So now we have basic operations, because Python doesn't automatically come with operations using complex numbers. So first of all, we're going to be storing complex numbers as a list, and we can see that in here we just have A and B, and A is going to be a real number and B is also going to be a real number. And we have addition, which is just we add the 2 A's and then the 2 B's, and when we add the 2 A's, that's the new A, and when we add the 2 B's, that's the new B. And for multiply, we have we kind of used FOIL to figure out the A. So the A is going to be the new A is going to be the first A times the second A minus the first B times the second B, and the new B is going to be the first A times the second B plus the first B times first B times the second A. And for square, we did something similar, and we have the first A squared minus the second B squared, and we have 2 times first A times the second there's only one A or B, so this is A squared minus B squared and then the new B is 2 times A times B. And I didn't write down the proof for this because we don't actually use this in this entire program. But I did write up the proof for this thing up here. So we kind of expand this out using FOIL, and we can I guess simplify. And when we have one of the terms we have to simplify is b times I to the power of 2, or b times I squared, and that just becomes b squared times -1 because I squared is -1. And when we do that, we get a squared minus b squared, and then 2 times a times b times I. And so a squared minus b squared is the new a, and for the new b we have 2 times a times b, and we take out the I that was here because b is supposed to be a real number. And anyways, that's why we have this for the square function. And distance squared uses the Pythagorean theorem to find the distance, and we just do a squared plus b squared. And if we wanted to find the distance, we would have to take the square root, but I called it distance squared because this is the distance squared. And the reason why I'm not square rooting it is because instead of square rooting it here, we can just square root, or we can square both sides of the equation. So we squared it in here, and the other time we're going to use this somewhere here, or in here, instead of having distance of nu z is greater than 2, I just squared both of these, and I have distance squared of nu z is greater than or equal to 2 squared, which is just 4. And the ratio and ratio reverse and multi-dimensional relocator are just so we can convert from the pixels to the A and B. So ratio just finds the length to the left of a point if the point was placed in a segment, divided by the length of the entire segment. And ratio reverse kind of plots first there's point old, segment old, and segment new, and it finds where the point new would be if the ratio for the point old and segment old were the same as the point new and segment new. And it kind of uses this function to calculate that. And multi-dim relocator just has multiple dimensions, but it's at the end the same thing as radio reverse, so it just runs radio reverse multiple times for each single dimension. And finally, there's also default color key, and this one takes in num, and in our case num is however many times we needed to run this in order to find if it was out. And this only is called if the point was outside, because otherwise it is just gonna be black, and this kind of uses honestly just random values that I tested until it kind of made sense. And yeah, it just takes the reciprocal of num plus 1, and it does a bunch of complicated stuff, but it doesn't really mean anything. And now we actually get to the real math, and this first function is Mandelbrot test, and it takes in z and iterations. So z is just the point we're testing, and iterations is however many times you're gonna run this equation. And what I did was, was create a list, and at first it's a list that only contains z, but zs or z's, and the reason why I chose z's is because it's like the plural of z. But anyways, zs kind of contains all the terms. So z is basically like the sequence that contains z0, z1, z2, and so on. And z, our original z, is z0. And we have a for loop that runs however many times iterations is, and every time we have something called new z, and this is exactly what this is. So we have we add a z plus the square of the most like recent term that was added, and that becomes new z. And originally I had something else where it was like new z, and then that's equal to new z, and then this was also new z, or no, I didn't have this line at all, and everything here basically was replaced with new z. But I decided against that because this one is like more clean. I'm pretty sure it's gonna take longer and it takes more memory, but I was willing to make that sacrifice to just make it mathematically accurate, or accurate to how I described it in here. And also it's gonna matter later. But anyways, it calculates the newest z, then adds the z to the list of z's, and then if it's further away than 2, remember these are both squared, then it's going to return false, and it's going to return the z's, and then otherwise it's going to return true, and then it's going to return the list of z's as well. And this is basically all the math that actually has to do with the Mandelbrot set, and the rest is just to kind of display it. So we have a class Mandelbrot, and when you run this, or when you call this, you get what you're seeing here. And yeah, it just shows the creation of a Mandelbrot set, and it also comes with the ability to like show the path of all the points. And Mandelbrot takes in the size, and this is going to be the width and the width and the height of the actual like surface, as it's called. And view window is the window we're viewing the actual numbers. So I guess this is the range of A, and this is the range of B that we are viewing. And color key, it just helps with the colors. And iterations is the detail. And visible progress enables the thing where it kind of shows it from left to right as it generates it. And first we have Pygame init, and this kind of just starts Pygame. I think you just need it if you want to do anything with Pygame. And next we have self.surface equals Pygame.display.set mode size, and this just creates a surface the size of whatever this was. And self.disp size is just a reformatted version of this, and what it does is it takes in or what it means is it's just a way of formatting the width and the height to work for the multi-dim relocator. And view window I already explained, and after it kind of saves all of the parameters, it runs self.mandelbrot grid, and when it's done, it updates the screen to make sure that the progress is shown. And actually this would make more sense if I moved it down here. And I just have this print to kind of show that if there ever is an error and there's like a black screen, then I can know that it's not just taking a really long time, and that it did finish loading everything, but it's just not working. And after we run this, we have a while loop, and it just runs forever until we actually close this program. So if we close this, we can see that the thing here indicating that it was running also ends, and this is responsible for that. And this kind of loops through all of the events that happens in a minute, or in an instant, I guess. And this kind of this recognizes when the user presses a button, and when we do press a button, it runs self.rootTracer. But before I explain self.rootTracer, let me just explain how Mandelbrot grid works. It iterates through all of the numbers from 0 to the height, and then pixel y. No, this is the width, and then all the heights, or maybe it's backwards, but either ways, we have A and B to represent the A and B in Z, and it finds that by having pixel X and pixel Y, and this is point. And currently the points are kind of in the form of the pixels, and so the first thing, the old window is going to be the window of the pixels, and then the new window, the one we want it to be, is going to be in terms of the actual corresponding numbers. So this is the view window, and because the view window goes from -2 to 2 for the height and also the width, what we see when we run the program is the Mandelbrot set when we look at it from -2 to 2 on both dimensions. But anyways, next we have ZS equals so this is actually, I'm gonna fix this to make it make more sense. The first thing that Mandelbrot test returns is see if it's in or not, in or out. I can't think of a better name for this, and or out. And in or out is just gonna see if it's in or out. ZS is gonna be however long it took for Mandelbrot test to, or however long this thing took to go off to outside the circle, or if it stayed inside, then it's just gonna be however long we tested it for, and like the results. And what we do is, if it was in, let's call it inside. So if this is inside, then we're just gonna create the pixel at that exact point it was inside. We're gonna color it black, and otherwise we're going to color it with whatever this returns, and we give it the length of ZS to help it, color it, and just so that it's not always the same color, and we can see how long it took for the point to go outside. And if self.visible progress, so this is just gonna see if we do want to kind of show it as it goes, and if that is true, then we do Pygame.display.flip. So we just update the screen, and we print done, and we have Pygame.display.flip again, just in case this was false. And the reason why this is here and not here is because if it was here, it would update for every pixel, but here it's updating for every column it finishes. And if we do it like this, we can see how fast it does. So it only takes like I'd say 15 seconds approximately. But if we did it here, it is super slow. It's running right now, and even I can barely see it. I'm not sure if you can even see it on through the YouTube viewing thing, but is super slow. And I'm gonna stop this. And even if we did make this an insanely small screen size, like 100 to 100, it's basically as slow as, I think I would say it's even slower than what we had before. I guess it was pretty quick, but it had to do 49 times less computing. So that's pretty interesting, I guess. And that's just because I guess updating this takes so much longer than anything else, and it's the same with print, but I assume that this is longer than print. This takes longer to run than the Python print function, but anyways, that's why I have it every column and not every pixel. And finally, we have root tracer, and this enables us to do what I ran earlier, or to do the thing where we can see the path it takes to see if it goes to infinity or not. The thing that creates the white dots and the white lines, and this basically runs the same thing as Mandelbrot test, but then now it has something called pixels, and it's the same thing as ZS, but it's just relocated into pixel form. And then we have self.shapes. This actually, I was trying to have this so that we could delete it every time, or we could delete all the shapes every time we create a new kind of route, but it doesn't really work. So I guess this thing, and this thing can be commented out. But otherwise, this loop iterates through all of the pixels that the root takes, and as long as the count is not 0, then it's gonna draw a right line through the first, or I guess the previous point and the current point, and it has the thickness of 2, and then we also draw a circle at the current point, and it has a radius of 5. And the reason why this only runs when this is not 0 is so that if it was 0, then this would be -1. And well, I guess that wouldn't result in an error, but because when you do like a -1 here, then it resets back to the very last thing, but that's not really what I want to do. So I only run this after 0, and it makes sense because there's one more circle than there is a line. But anyways, after all that, it flips the display. And yeah, that's about it for this video. And as always, I will put the program in the description. And thanks for watching. Bye.